Okay, let's get our slideshow set up from this slide. And let me make just a couple of, hope fairly minor announcements, but this is not working. That's not good. There we go. Guess something was sitting on something. Okay. Sorry about this announcement, but I need to say it to all the classes. This class, I'm in better shape than most. We have been working for weeks now on spring and summer schedule, and it's still a terrible mess. I've got a lot of it straightened out, but goodness gracious, the rest of it, well, most of the rest of it's not too bad. I'm on one more class that is just horrendous, and hopefully I'm going to finish that today. And if I do, then I get back to grading papers. These are what have stacked up since I've been working on the spring and summer schedules. Wait, I said that. That takes care of spring. I still have summer to do, and that's probably still going to be a big mess, but at least I have a little more time to work on that one because we won't be registering for summer until mid-spring. So I'm going to let that one slide a little bit. I hope they're not letting students register for summer now. Otherwise, it's going to be a big mess. But anyway, so if I'm this far behind on grading, I'm even further behind on putting things on blackboards. So that's why you haven't seen me score. They've been graded, but I haven't had any opportunity to sit and do anything on blackboard. So, like I said, I'm hoping this week to get the spring schedule finished, hopefully maybe even today, and then I'll get back to grading. But you see, I picked up in the second mini-term, I lost a medium-sized to good-sized class and picked up a big class for physical science second mini-term. And that's what a lot of this grading is stuff I haven't even gotten to do for them. I've been trying to keep some of it moving along well. Oh, I forgot the other page word problem. Okay. All right. So anyway, hopefully, maybe this week I'll start catching up some of this backlog. All right. Any questions? Anything we've covered so far? Okay. We did example 1 last time, but I'm going to have to use the same slide here because example 2 is not given in the text. So if there are no questions, we'll get started here. I have a feeling. We'll have these interruptions periodically for a few minutes, hopefully, and not too much longer. Okay. Example 2, top of page 467. This is Chapter 7, Applications of Integration, 7.3, determining volume using the shell method. Okay? And here's what the problem asks for. Find the volume of the solid form by revolving the region bounded by the graph of x is equal to e to the minus y squared. Okay? About the y-axis, that's not quite the right symbol. About the y-axis. Okay? It's supposed to be a y-axis. Within these ranges, 0 less than or equal to y less than or equal to 1. Okay. Oops. No, I'm sorry. I misread the problem. was going to say that doesn't sound good. Okay. Find the volume of the solid form by revolving the region bounded by the graph of this and the y-axis between 0 and 1 on the y-axis, and revolve that about the x-axis. Now maybe I've read the problem correctly, at least partially. So generally on this, you almost got to draw a picture. Sorry about that. This is going to take up way too much room, but we almost have to do it. Okay. We only have to go, I still haven't drawn this right. Let me start over. Okay. I still have it in my head. We're going around the y-axis. We're going around the x-axis. Okay. All right. Now, we're going between y is 0 to 1, so we're going to do that. So if it's going around the x-axis, we're going to go down to -1. Okay. Now, let's plug in a few values here. Okay. X is equal to minus y squared. Okay. Usually we're thinking of y as a function of x. Here, x is a function of y. Okay. So let's pick a y. Any y between 0 and 1, including. Second? 0, my favorite. Okay. So when y is equal to 0, what's x? Y is equal to 0, what is your x? 1. 1. Okay. So y is equal to 0, x equal 1. So there we are right there. All right. Well, let's move up to, none of the others are going to be particularly fun. They're all fun, but let's do y is equal to 1. And what would that be then? Now, pull out your calculator. I don't expect you to do it in your head. What would that be? Y is equal to 1. The e to the minus 1. That's basically about 1/3. A little bit greater than 1/3, perhaps. Something around there. Don't you get it? Or do you?
We got 0.36.
Yeah. A little bit more than 1/3. Okay? Now, what's it's doing in between there, I really don't care too much. We're just going to make sort of a curvy type thing there, just to try to make it look like the book. Okay? Now, there is the function. Okay? Okay? Also bounded by the y-axis over here, so that's as far as it's going to go here. And you're only going between y is equal to 0 and y is equal to 1. And this is all going around the x-axis. So we're going to revolve this around the x-axis. So basically, the shape will be like this. Okay? That would be, this is a solid revolved around this way. Maybe I should have done all the arrows the same way. Okay. Now, that's not particularly clear, perhaps. Okay. Now, one tendency might be, since you're going around the x-axis, to do a dx here. But then, you're going from, you have to solve this function here is x is equal to e to the minus y squared. I'm not particularly fond of trying to get this as a function of y. In fact, that looks like it would really stink pretty badly. So I think what we have to do with this one, we're going to have to take our dy's because we already got this in terms of y. Right? So therefore, if we take dy's and you're going around here, that's going to be a cylindrical shell. Okay? Not going to be disk. Disk look like that might work, except you would have to have y as a function of x here. You know, because you have to have this value here in terms of x, not in terms of y. Okay? So, shells have got to be. Okay? So let's just do a representative shell here, right there. That's going to be a dy. Okay? Now, what's the volume of that shell that you would have going around there? And I don't particularly care for this too much, but it seems like a pretty good place to use it. dV, that's that incremental volume, that little piece of a volume there. Okay, that little piece of a volume, I've got a dy, that's a part of it. Okay, obviously the length of this is going to be a part of it, right? And we've got that length as a function, that's your x length here, right? And that's already as a function of y. So that's pretty good. Okay? So there's your length times the width. That's going to be the area of this little strip, right? And then we've got to do that strip around the x-axis. Well, that's just going to be y, isn't it? So that's your radius of y. All right? So your length times your width times 2 pi r, because that's going to be a circumference around there. And the radius there is going to be the y. Does that make sense? Okay. So dv is going to be the length, which is e to the minus y squared dy. And then you got a 2 pi, and your r here is going to be this length here. And that's just simply y. That's the radius. So that'd be 2 pi y e to the minus y squared dy. And this then is going to be what we're going to integrate. Okay? Now, I'm going to do this. I'm going to regret doing it. And we're doing, your dy's are going from y is equal to 0 to y is equal to 1. Okay? That's your increment, so it's going 0 to 1. Now I'm going to change that ever so slightly. Okay? This is just going to give you your volume. It's going to be, I'm just going to bring the pi outside, okay, and go 0 to 1 of 2y e to the minus y squared dy. Does anyone see why I wanted to keep the 2 inside? With this weird little notion of mine. Say again?
The 2 and like the negative y's.
Okay, when you take the derivative of this, you don't need a 2y there. It will be a negative, you're right. So we'll take care of that in a minute. But I'm thinking, what's the technique for solving that? Okay, you picked up your fourth file, so I'm going to substitution. Never mind. Okay. Done. Okay. All right. Looks like substitution will be the thing on this, right? Okay. So, what might we substitute?
U equals e to the negative 2?
I wouldn't say e. Let's just do negative y squared. You see kind of why? E is your function there, and the innermost part of your most complicated part of the problem. E's that complicated part, so let's do the innermost part of that. Okay, then what would be the next step? du equal
negative 2y.
One more thing.
dy.
dy. Okay. Now we've got almost exactly what we have here with the exception of one little piece. What's that? Negative. Okay, so let's just move the negative to go with the du. Okay. Now, the pi's still there. That's good news. Okay. The integral here is going to be a minus, and that's going to be from, we also have these limits are for your y. We need to have limits for u when we go to this new thing. So when y is equal to 0, what's u equal to?
1.
Y is equal to 0, u is equal to
Negative
1. Y is equal to 0, u is equal to 0 squared is?
0.
0! All right, okay. And when y is equal to 1, u is equal to?
1. Is it a negative 1?
Negative 1. Yeah.
Okay,
So
so I thought the square.
plug a y in here, 1,
Right.
and u becomes a negative 1, right?
Would the square not?
Yeah, that's what I was thinking, the square.
Okay. Let's square 1. And what do you get?
I was supposed to square the negative 1. I see what you mean.
Yeah.
With the negative ones.
Okay. So u becomes negative 1. Which isn't too bad either, because now this goes from 0 to minus 1. And let's see what else. We already pulled the negative on the outside, and the du was the 2y dy, so that's just e to the u du, isn't it? Yay or nay? Because your u is minus y squared, so that e to the minus y squared is e to the u. The du is a minus, or minus du is 2y dy, 2y dy, so that's your minus du, and pi is just out there. But, what do you notice here? You like going from integrating from the big to the small, or don't you like going from small to big?
Small to big.
Okay, and if you reverse these two, what does that do to your sign? If you're doing the area from here to there, that's negative the area from here to here. Right? So that changes the sign. So there goes the minus sign. That's disappeared now. So now we're doing pi times the integral from minus 1 to 0 of e to the u du. See what we did? We flipped the sign, the limits, and that took away the minus sign. Okay? Now let's do the integral. The easy part, right? It's going to be pi antiderivative of e to the u du.
Log?
You're taking the inverse of it. I want the antiderivative of it. Oh.
Look it up.
My favorite function of all time, and y'all can't remember how to do it. Okay, let's do this. What would be the derivative of e to the u? Say again?
I was just trying to work it out in my head. I'm not sure. Usually times e, so it's going to be like
Yeah, here. I'm sorry, I couldn't hear.
UE. I'm trying to figure out. It's when u is going to be multiplied by the e, and then
Okay, it's not multiplied. U is the argument of e. It's e raised to the u power.
right.
Okay?
But when we take the derivative of
What's that?
but when you take the derivative of
Okay, but think of the exponential function as a function. It's one of the most tremendous functions in the world. It's called, it's the base of our number system, not base 10, but The natural base of the number system is e, right? 2.7 blah, 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 blah. You know, it's an irrational number, a lot like pi. Only it's more powerful than pi. What's the derivative of e to the u? Looks like you had it, but you don't. No. Oh my. And where we spent all that time in chapter, what was it, 5? Go back in chapter 5. Oh, here it seems like this would be a good place for it. Maybe not. Yes. I just happened to turn to page 378. Look at basic differentiation rules for elementary functions. And number 10, our favorite of all time. What's the derivative of e to the u? E to the u. Okay. So what's the antiderivative of e to the u? E to the u. All right. How could we forget that? That's our favorite.
How is e like the basis of our numbers?
Well, no. Well, e is the basis. Well, in calculus it is, because of this. The derivative of e is e, and the integral of e is e. It's the basis of our of calculus. It's the base number, and that's why they call it the natural log, because it's base e. You know, everything just works out so nicely if you have that as your base. I don't know why. Euler probably found it fascinating when he discovered it. I don't know if he or somebody else named it after him. That's why it's an E for Euler. It's E-U-L-E-R. And that's why they named it.
It's sort of like the beginning and the end, because it is itself. And it,
right.
You know, that's
yeah. Oh, and there's lots of little formulas that can come out of it that are just about incredible in their simplicity, but in their depth of what they mean. And there's Euler's formula is one, and let's see if I can remember it. I may have it wrong. E to the I pi, or maybe it's pi I, however you say it, is equal to -1, or something like that. It's just, it has in it our two irrational numbers, our imaginary number, and -1. Okay, I don't know if that's absolutely correct, but it's something like that. Yeah, it's called Euler's formula. It probably is in the book somewhere. Let me see if I can find it. Probably the index will be better. Index of applications.
E to the I times x is equal to cosine x.
Yeah, that comes from it. Let me see if I can find it. I'm not certain it's in here. It should be. Oh my, it may not be in here. It has Euler's constant and Euler's method. 6:15. I shouldn't be spending time on this, but close.
E to the I times pi plus 1 equals 0. So
Say that again.
E to the I, my screen's cracked, but it says E to the I times pi plus 1 equals 0. So that would be what you have.
Yeah, and that's equal to -1. That's it. Yeah. They say it somewhere on this page. Oh, that's Euler's constant. That's not it. But yeah, that's it that you found. Okay. Euler's method is, yeah, that's something else too. Okay, I'm surprised it's not in here, but okay. But anyway, what is? Okay, now we're doing this. The pi's on the outside. What is the antiderivative of e to the u? E to the u. evaluated from -1 to 0. Okay? So that's going to be pi times, and e to the 0 is 1 minus e to the -1. Okay? That is your answer. Okay? You could rewrite it as this, pi times, let's make that, bless you, e minus 1 over e. That is another way to write that same answer. A little bizarre to do it this way, but if you think of this as 1 over e, so this would be e over e minus 1 over e, which is e minus 1 over e. So that's another way to write it. It's not any better than what we just did, but it just doesn't have a negative exponent. Okay? They left it in the book, pi times 1 minus 1 over e. So they just did this to it. Pi times 1 minus 1 over e. I just took it one more step. All right. Here's Catherine. And ding, ding, ding. Perfect attendance today. Finally again. We started off really strong that way. Sort of fell off in the last few weeks, but we got it back today. Way to go. All right, we're just finishing example 2 in the text on page 467. And they actually evaluate it, tell you what it is. Something just short of 2, amazingly, 1.986. Wanted to plug those numbers in. All right. Any questions on that? Please, folks, remember how to integrate and differentiate exponentials. They're so easy. All right. Now, there is a little exploration gray box in the middle, or almost the middle of page 467. It says, to see the advantage of using the shell method in example 2, solve that equation, x equal e to the minus y squared for y, and that is a mess. Okay? It's doable, but when you're going from here to here, that disk, that's just 1. So that part is easy. This part here to here. So that's going to, what value is that again? E to the minus 1, I think is where that's going. Yeah, e to the minus 1. 1 over e, which is about 0.36 or something like that. Okay, that part wouldn't be bad to do this method. But then this part, and they show you in the text what it would be, the square root of minus log x, but x has to be between 1 over e to 1. Certainly it couldn't be anything greater than 1, because you'd be in pretty serious problem there. You would have a negative number under your radical, and you can't do that. So that would be, and then to imagine trying to integrate the square root of negative log. Okay, that would be an awful thing to try to do. So far easier to use the shell method on this one. Okay, let's get through this and go to our comparisons. That was example 1 that we did last time. I was just using that slide. Here we are. So let's look at the comparison of the disk and the shell methods. Okay? The disk and the shell method can be distinguished as follows. For the disk method, the representative rectangle is always perpendicular to the axis of revolution. Okay? That's why I said that was attractive at first, because your axis of revolution this way it would have looked like a disk would have been a great thing to use, except it was such a terrible function to have to deal with. The square root of a negative log. You got it. Okay. Whereas the shell method, the representative rectangle, is always parallel to the axis of revolution, as shown here. So here we have a vertical axis of revolution. You see there's your axis of revolution there. And this representative thing goes around that. That would definitely be a washer. You know, not quite a disk, but a washer. That's the difference of two disks. So that would be pi r squared minus pi r squared. You know, long, big r minus little r squared. Okay. Now, going around the x-axis, if that was our strip, again, that makes for a washer. Pi big R squared minus pi little r squared. Two disks, one subtracted from the other. But for the shell, here we have the axis of revolution there. Here's our strip. That's going around the axis. That makes a shell. It doesn't make a dish or a washer. Okay? And same thing here. If that's your representative slug, and you're going around, say, the x-axis or something like that, again, that's making a shell. Okay? So that's what gives it away which one we're going to wind up with. The other part is a choice of why do you choose that, and that would be, depends on how the function's defined and what it is, and which way is going to be the easiest way to do your the D's, the little slivers. Okay. So let's do example 3. Now, if you go to larsoncalculus.com, you can see an interactive version of this type of an example. And you can certainly go for it. So it says, find the volume of the solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1, y is equal to 0, x equal 0, and x equal 1 about the y-axis. Okay? Now, on first reading, looks like to me we want to do dx's because the function is given in terms of x. Now, you can change this and solve that for x in terms of y, and then you can do your dy's. But that's going to turn out to be a sort of a nasty thing. That's going to be x squared is equal to y minus 1, you know, and then take the square root, and you're going to have a plus and a minus, and that just gets messy. This is a pretty simple function here. So it looks like to me the best thing is to choose a dx. But let's see. Okay, find the volume of the solid formed by revolving the region. Okay, we're revolving around the y-axis, so I need to have something like this. And y is equal to x squared plus 1, so let's pump a few points in here. I don't need many. Probably don't need this many, but let's just see. Okay, let's just do a few points, like x equals 0. What will your y be? 1. Okay, there's 1 point. And x equal 1 would be 2. Okay, and negative 1 would also be 2. Okay, so we have a parabola going up like this, right? All right. Find the volume of the solid formed by revolving the region bounded by that y is equal to 0. Y is equal to 0 is down here. And x equals 0 and x equal 1. So that's what we've got, this little bit right here. And we're revolving that around the y-axis, so it's going around like this. Okay? Now, which did I say looked like it might be the best thing to do? Dx. So if you do a dx here, what kind of method are you going to use? Okay? Notice here, here's your strip with dx, right? And it's going around the y-axis. that's going to form a picture of that. This thing going around the y-axis. That forms a
Applicable. Well, I'm thinking based on the shape, but it's
this strip here, this dx here, going around the y-axis. That forms a not a disk, a shell. It forms a shell. You see it's coming around, going like that. A disk would have been a dy here going around this like that. That would have been a nice little wheel, you know. Been fine. But we don't have that in terms of y. We could get it in terms of y without any problem. But you see, if we did the dy's here, the first part of these would be here. That disk would be easy. There'd just be a thing from 0 to 1, 0 to 1. You know, that'd just be a block there. That would be easy. But then you have to do 1 minus the square root of 1 minus y. Yeah, 31 minus y. And that's just a lot messier. Okay? You did the strip here. The height is the y value, which is that. The thickness is your dx, which is that. And the radius would be x, right? So everything's in terms of x, and it's pretty easy to do. So to me, this is a shell method problem, without a doubt. Okay? Easiest to do. You can do it the other way. Okay, and what is that shell? It's the integral. And if you're doing dx's, x's are going from 0 to 1. So 0 to 1. You're doing their dx's. That's what we thought. The height of that rectangle, the thickness is dx. The height is your y value, right? You're going from that function. This function is y is equal to x squared plus 1, right? So that would be x squared plus 1. Okay. There's your dx. Okay, that's that little rectangle right there. Y tall, dx thick. But it's going around the y-axis forming a shell, so that's going to be a circumference of, radius of this distance here. Well, that's simply x. Okay? So that would be x times x squared plus 1 times dx, but of course you have a 2 pi out here, don't you? Except, again, in this case, no, I think I'm happy with it, the 2 pi on the outside there. Okay? You could do it using that on the inside and doing a substitution, but it's just as easy to go on and do this one. So how would you solve that integral? Do you agree that's the integral to do? Okay? The little strip is dx times y, and the y is x squared plus 1. And then you're going to take this and go around the y-axis, so that's the 2 pi r. That's the circumference, 2 pi r. 2 pi being out here, r being your distance from the y-axis, which is x. So everything's in terms of x, except the 2 pi, and that's on the outside. So, how would you go about doing the antiderivative here? 2 pi integral 0 to 1.
Would you distribute your x first?
I would. That's exactly what I would do. X cubed plus x dx. And that's pretty easy to integrate, isn't it? Be the antiderivative of x cubed. Anybody? X to the 4th over 4 plus x squared over 2, evaluated from 0 to 1. You know, that'd be 2 pi. I think I can even do the substitution pretty easy. What would that give you? Anybody? Anybody? Pretty easy, huh? 1/4 plus 1/2. Anyone know what that is, by the way? Oh, minus 0. I did that, sorry. Okay. That's 2 pi times, what's 1/4 plus 1/2? 3/4. Oops. 3/4. Goodness gracious, can't write. Okay, the 2 will go in the 4 twice, so that would be 3 pi over 2. That's what I get. Let's see, do they get it? Oh, look at that. They got 3 pi over 2 as well. Now,
how was it that you get the 2 pi?
second,
How was it that you got 2 pi?
2 pi? Where? Oh, here? Oh, this one, right here. Okay. Because you're taking this strip and going around the y-axis. All right? That strip's going around the y-axis. Well, how far does that go? That's going to be a circumference, which is 2 pi r. So the 2 pi's out there, the r is merely your x-value. See, that's the radius. I can't do a circle with a flat board, but if you went out, in, back out again, that distance of travel, that strip traveled is 2 pi r. R is your x. Whatever that is. Make sense?
Yes, sir.
Needs to make sense. No guessing. The key is to get that element, okay? That element is the dx this way or y that way, okay? Then, what is it doing? It's going around the y-axis. That's making a shell around there. And how far does it go? It goes its circumference around there. And circumference is 2 pi r, where r is just your x. That's how far it's going around. Trapping out the volume as it goes. And then you're integrating from 0 to 1 on the x-axis, so it's the dx here. And that gives you all those little strips starting from 0 going the way out. Gives you a total value of 3/2 pi. 3 pi over 2, however you want to say it. Now they did it the other way too. They did it with the dy's. And when you do the dy's, then that's a disk. And the disk from 0 to 1, pretty easy. It's just the area there is pi r squared, where the r is 1, so it's pi times 1, because that's the thickness of it. So that would be just pi is that part. And then the second part is the nasty part. 1 minus, and you have to get this function in terms of y, not in terms of x, because you're doing dy's. So that would be square root of 1 minus y squared. No, square root of 1 minus y. Square root of 1 minus y is this measure, and you're going 1 minus that. 1 minus square root of 1 minus y. And you can do that. It's easy enough to do. Well, kind of. But it's just a lot messier integration to do. I go first from different classes through at 11:40. So from 11:40 until 12:15. What are you wanting to finish with this? Oh, okay. So that's one from 11:40 to 12:15. But then the bigger chunk of time is between 2 and 6. So either one of those. You know where my office is? Okay. All in my office door. Right there. I have my locator card there. Okay. So if you want to see me do the other integration, I will. Or you can just read it from the book. it's doable, but it's just not a very pretty sight. Oh, it actually isn't as bad because remember that's pi r squared because you're doing a disk, area of a disk, and that square root of 1 minus y, then that's, when you square it, it just becomes 1 minus y. So it's not nearly as bad as I was saying it was. But it is longer to do, and I don't know, the calculation is just, you have to do it in 2 pieces, all that kind of stuff. All right. Now, any other questions there? Oh, let's see how they work this one. I guess they're going to show you. So, sorry about that. I'll let them show you how they do it. Okay, the first, find the volume. They're going to do the washer method. Well, it's the disk and the washer method. This part down here, when you revolve this around the y-axis, okay, that gives you a disk. Okay? And then this part up here is going to be a washer. It goes from here to there. So that's going to be a washer around there. So it's a disk slash washer method. They say the washer method requires 2 integrals. It does. The first one's really easy because you could do it without even doing an integration because it's just a geometric shape. The volume of a cylinder. Okay. So, but they do it. Okay. So what they do for the first one, doing a dy here, they first have to get this in terms of x. So y minus 1 is equal to x squared. Take the square root of that, and you have x equal to the square root of y minus 1. So that's the little r up here. Okay? The big R is just 1. Okay, that's your big radius. Down here, all you have is that radius of 1. So this is really from y is equal to 0 to 1, and that's what you're integrating when you do your dy here. 0 to 1, you just got that cylinder. Pi r squared h. Pi times the radius is 1, 1 squared is 1, and h is 1, so it's just pi. That just gives you pi. Now they're going to work it out a lot more detailed than that, but that's all there is for this bottom part. Then the top part is 1 minus, okay, pi times 1 squared, okay, minus times dy times pi times this thing, which is this thing squared. Okay, that's your little radius, and that's what you're subtracting off. And when you square that, you just do y minus 1, so you have pi times y minus 1. So that's going to lead to your integrals, which they do here. This one, why they do this, I don't know that they do. The integral from 0 to 1 of pi times 1 squared dy. 1 minus 0 squared. Yeah, that's really worth doing. I mean, it's just pi. That's all that is, okay? This is just 1. 1 minus 0 is 1. So that would be y from 0 to 1 would be 1 pi. Why in the world they make a big deal of it? But then the next part is this integral from 1 to 2, because there you're doing from 1 to 2. I forgot to point that out to you, so let me go back and do that. Okay. When we were doing the dx's, that was just 0 to 1. That was pretty simple. Here we're doing this thing revolved around here, and that's going to be 0 to 1 here when you're doing your dy's, and then 1 to 2 here when you're doing those dy's. So that's why you have the second integral there, and it goes up to 2 with before it did. So from 1 to 2, and then the outer radius is 1 squared. It's pi times 1 squared. That's done. Minus the square root of y minus 1 squared. Now, you might say that wasn't what we had. Whoops. We had, no we didn't. Okay, sorry. Yeah, y minus 1. Okay, I was thinking we had 1 minus 1. y minus 1 squared. But that's pretty easy to do too, because when you take square root, you just get y minus 1. Okay? So 1 minus y minus 1, that's just going to be the integral of y from 1 to 2. Pi times that. So, and that's exactly what you got here. Pi times the integral. I'm sorry. It's minus a minus 1, so it's a 2 plus 1, 2 minus 1. It's 1 minus y, because when you square this, it's y minus 1. 1 minus y minus a minus 1, which is another 1, which is 2. So 2 minus y dy. So there's your integral in the second part, which again is not a hard integral to do. In fact, they're a really easy one. So the first is just going to be pi. Why they go into that much detail on it? First one's just pi. The second one is going to be the integral of 2 pi minus y squared over 2y times y squared over 2. Evaluated from 2 to 1. That's just a little more calculation, but it's not bad. That would be 2 times 2 is 4 minus 4 over 2. So 4 minus 2 is 2. Minus 1, so that would be 2 minus 1 half. That would be 3 halves. Okay, and so here we have 4 minus 2 minus 2 plus 1 half. Because remember, this is the lower limit, so it's the minus of that. So minus 2 plus 1 half. This all has the zero, and it's just 1 half pi. So pi plus 1 half pi is 3 half pi. So many more little opportunities to make errors. So that's why the shell method just works so much nicer on this one, because it was just one integration, not two. No pieces to deal with, no subtractions to deal with. It was just a lot easier to do. Okay, so here was their solution, which is 3 halves pi. Okay, that's the disk method, or the disk/Washker method. Okay, then doing the shell method, which you think might be a little harder because it's got 2 pi r rather than pi r squared. I mean, that's not that much worse. But it's this strip. The height of that is just merely your y value. Okay, so that's your x squared plus 1. Your thickness is dx, delta x, I showed here. And then the radius, the 2 pi r, that r is, the radius is just that x. Or they use p rather than r, I'm not sure. And you're going from, since you're doing dx, it's only going from 0 to 1. Not two pieces, just one piece, and it's done. Okay? So here's your 2 pi r times the integral from a to b, which has to be 0 to 1, of your radius function, which is x, times your height function, which is x squared plus 1. Well, yeah, x squared plus 1 times dx. It's just such an easy integral to do, 2 pi integral from that. And like you said, go on and multiply, distribute the x through there, x cubed plus x, integrate that. There you have it. Same thing we got, 3 halves pi. In every way, I think, easier to deal with. Okay. Whoa! That was example 3. Okay? They are not doing example 4 or 5, so let's go and do that. Any questions on this before we lose it?
Would it still work out if you didn't distribute your x?
Sure. Yeah. What I would do then, I'd pull this 2 in here, leave the pi out there, and have this as your u, and that would be your du, right? And you can do it that way too. Is that what you had in mind? That's when I first glanced at it, I thought that's what I want to do. I thought, oh, this is easy to distribute. Especially when you said distribute. I said, yeah, works well. Okay. You want to see that done? Okay. Oops. I did it again. All right. Let's do example 4, top of page 469. A pontoon is to be made in the shape shown in this figure, and it's designed by rotating the graph of, goodness gracious, I got to sneeze. Sorry. Y'all awake yet? Okay. Designed by rotating the graph of this. Y is equal to 1 minus x squared over 16. That's an ugly 6, isn't it? Okay, 16. In between minus 4 less than or equal to x is less than or equal to 4. Okay. About the x-axis, where x and y are measured in feet. It says find the volume of the pontoon. All right. I can tell I'm going to love this problem. Okay. I guess what we have to do is draw the graph. So let's do that. We're rotating about the x-axis, if I remember right.
So now this one will be the disk.
Second?
This one will be the disk.
Different?
No, the disk.
Disk. Yeah, I believe you're right. Yes. Okay, so let's draw it. Let's let x equal 0. And what do you have?
1.
1. So y goes from plus 1, and you know it's going to go to minus 1 because you're going to rotate it around the x-axis. Okay? Okay. When x equal 2, what do you have? Oh, I'm sorry, x equal 1.
15/16.
Second?
15/16.
15/16. So it's almost 1. Not quite. How about when x equal 2?
3/4.
Yeah, because that would be 4/16, which is 1/4. So that would be 3/4. So you're not coming down too much. And when x equal 3,
7/16.
I believe you're right there. That's yeah, 9. Yeah, yeah. All right, 7/16, so a little less than a half. Okay, and then when x equal 4, 0. Okay, so same thing on the minus side. So it's going to be, I don't quite have mine drawn properly. When you revolve it around the x-axis, you're going to get that pontoon there. And if you were saying, let's do your dx's, right? Absolutely. Okay? Do your dx's and do the disk method. That's going to be disk, not even washers. Okay? Because you're revolving this around the x-axis, right? And there you have it. Now, your thickness here is dx, of course. Your height of this thing, now we're only doing the upper side. I've been drawing the lower side, but we're only doing the upper side. That's your y, okay? So that's your radius, okay? And then you're doing revolving that around here, so that's just the area of this disk that you had here is pi, that's the radius, okay, r squared, okay. Now, here's the good news, folks, or part of the good news. whatever you do over here is going to be exactly like what you do here, right? So let's make it simple and just go 0 to 4 and double it, right? Because the volume here is going to be the same as the volume there, right? So let's just do 0 to 4 and double it. Save ourselves a little bit of work, and I always enjoy evaluating at 0. It's one of my favorite pastimes. Okay, so what we have then, let's do that disk that I just sort of drew for you here, at least drew part of it. That disk there, okay, going to be the integral, and your length here is going to be your y, that's your radius. So we got pi times that radius squared, so it'd be 1 minus x squared over 16 squared times dx, okay? And that's going from, you have a 2 out here because we're going to double it, 0 to 4. Okay, now let's make sure that makes sense. The height here is your, that's your radius, that's your y, and y is exactly, this. So the pi times that radius squared, that's going to be the area of this little disk here times dx, and you're going to integrate that from 0 to 4, and we're going to double it. So that's what gives it. Now, the only part that's sort of nasty here is squaring that thing. And that's not particularly a pretty sight, but it's all doable. There's nothing wrong with it. That's going to be 2 pi times the integral from 0 to 4. Okay? Now, what is that thing squared? Anybody? Anyone? Well, it'll be 1 squared, won't it? Oh, good. Okay. Minus twice the product of the 2, and twice the product of those 2 is going to be minus 1/8 x squared, right? Right? This is the part that really stinks. Plus x to the 4th over 16 squared. I think that's 256, isn't it? Someone, if you got a calculator, square 16. Is that right? All right. And then that's going to be times your dx. So that's going to be 2 pi. What's the antiderivative of 1? dx.
1x.
X, exactly. Minus, and then the next part. Antiderivative of x squared. Let's just do it that part first.
X to the 3rd over 24.
Yeah, 24. Because 3 times 8, okay? And then plus, and this will be
X to the 5th over
5 times that. Yuck. Okay. That'd be a 30. That would be a 8, right? 1280. Okay. And we're going to evaluate that from 0 to 4, which doesn't look like a lot of fun either. That's going to be 2 pi. All right. When x is equal to 4, that would be 4 minus 4 cubed is, I think it's 256 again, isn't it? Divided by 24. Yuck. I'll just leave it 256 over 24 plus, and this gets even worse, 4 to the 5th power divided by 1280. Second? Okay. And I'll do the 0 part. So what the total of this becomes then? Is anyone? Not something I can do in my head easily. I don't think I can do it at all, but I think I probably could if I really strained really hard on it. Because 256 is 2 to the 2, 4, 8, 16, 32, 128. With calculators, go and figure that out.
16 thirds.
16 what?
16 thirds.
What is that? Just the 256 over 24?
So that was 12.
It's what?
Let me start over off and do it right. 4.
You may be right. I don't know. I just was
I
asking.
don't think I am.
Okay. Let me start over. 2, 4, 8, 16, 32, 64, 128, 256. That's 2 to the 8th is 256. Divided by 24 is 2 cubed times 3. So that would be 2 to the 5th divided by 3, and 2 to the 5th would be
I got it again. 16 over 3.
the total answer at the end. 16.
It'd be 2 pi times 16 over 3.
Oh, 2 pi times that. So that would be 32 pi over 3. Is that what you said? All right. Let's see what they got.
29 over 15. Oh,
They got 64 pi over 15. These are the kind of calculations.
yeah, we didn't double ours, did we?
Well, that's what the 2 pi is. Yeah. And I mean, I just don't have a calculator with me. 256 over 24. That's 2 to the 8th divided by 2 cubed. That's the 2 to the 5th over 3. If I can do this. 4 minus 2 to the 5th over 3 plus, yuck. That would be 2 to the 10th, I believe, over to the 5th, 2 to the 6th.
No, I got 28 over 15.
28 over 16?
Over 15.
15. They got 64 over 15 pi.
Well, mine would be times 2 pi. 28 over 15 times 2 pi. That's still not right, though.
All right.
You want to try that one?
Yeah, I mean, if you want to, that'd be fine. Just, okay. I'm just going to do this part right here. Okay. That'd be 4, minus 256 divided by 24 plus 4 to the 5th
Now I got 32.
You did get it?
Yes, sir.
32 pi over 15?
Well, no, it would be 64 pi over 15.
64 pi over 6? Yeah, that's what we got. Okay. I think it comes out right. I just don't know exactly how to do this on your calculator. This would be a way to do that, and I just don't know how to do it. So, we'll leave that. You got it, and it worked out. Using these numbers, right? Yeah. Okay. I knew it would. It's just it's a pain in the neck. Yeah, because this. That's 25 thirds, I think it is. No, 2 to the 5th over 3. And this would be 2 to the 10th over 2 to the 6th times 5. And so that would be 2 to the 4th. So 4 minus 32 thirds plus 16 fifths, I think it is. And then I'll be in class at 1, so from 2 to 6.
Okay. Absolutely. Thank you.
Okay. Okay. If I've done the math quickly in my head right, I think this is what it comes up to. Least common denominator is logically 15. And this would be 60 then. 60 minus 5 times 32 would be, yeah. I'll take your word for it that it works out that way. I believe it does. Okay. Now, they mention here the shell method. If you tried to do that with this one, oh my word, what a mess. That would be your dy's here, and it's going from here to there. That means you have to solve this in terms of x is the function of y's, and that would be a mess. An ugly, 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 ugly mess, okay? So you don't want to do that, okay? It's doable, perhaps, but it's still a mess, okay? And then evaluate an integral that requires a u substitution, so it's sometimes terrible. There are some you can't even do by one method. Totally impossible. You don't have a way you can. So in that case, try to go for the next one, which is, I think, what we're going to do with example 5. Okay? So let's do example 5. All right. Find the volume of the solid formed by revolving a region bounded by the graphs of, oh yes, y is equal to x cubed plus x plus 1, one of my favorite functions of all time. Y is equal to 1 and x equal 1 about the line x equal 2. Okay. So here is basically how this one's going to look. I don't need this much space, but just to give it. Okay. Y is equal to 1 is going to be here, minus 1 is going to be here. Woo, yeah. x equal 1 is going to be here, x equal 2 is going to be here, x equal minus 1 is going to be here. I don't think we need that at all. So, y is equal to 1. That's that line. X equal to 1 is that line. And we need to do this function between 0 and 1. Okay? When x equals 0, y is equal to 1, right? When x equal 1, y is equal to 3. Right? So I have a feeling this is doing something like that. Probably not exactly that, but something kind of like that. Okay. And we're revolving that around the line x equal 2. So this megaphone here is going over to here. This will be x equal 3 will go up like this and then down like that. Something like that. So this is going around that. Okay. That wedge revolved around this line x equal 2. Okay. Now, if we wanted to do a dy, that means we got to get this thing x as a function of y. Good luck with that. Because this has the cubes in linear terms, that's not going to work. You will not be able to get an analytical solution for that. So that means we better, I'm sorry, I said, so we better do our dx's. And the dx in this thing is going to be what? What method? We do, well, actually, here's your dx. What is that going to be? Revolving that rectangle around the line. That's a shell method for sure, and there's no way around it. No way to do a washer method with this one. I don't think. I don't think there's any possibility at all. So let's see what our shell will be. You're going to be integrating the height. Okay, we know it's going to be a dx. Okay, that's going to be the thickness. The height of this is going to be your y value, which is x cubed plus x plus 1 minus 1, because it's starting from here. So minus 1, that's just going to wipe that one out, right? Subtract off that 1. Okay? Then you got your 2 pi r, and what's your r? Ooh, okay, now this is a different type of thing. Your radius here is from 2 minus your x. You see? 2 minus x, that's going to be your radius. You see that? 2 minus x, subtract off that part, that's the radius that is around. Okay? So, 2 minus x. X equal 2 to x equal x minus, yeah, okay. Yeah, okay. And that'll do it for us. So, that'll be 2 pi times the integral. Oh, and where's your integral at? X is going from 0 to 1. I believe that's right. Okay. And let's do that multiplication first. And here I think this is the way to go. Multiply it first. Don't try to come up with a way to do it otherwise. So if you do that, that's going to be 2x cubed, right? Minus x to the 4th plus 2x minus x squared. I think. Okay. I'm doing it fast. And there's nothing you can simplify that. So there's no, I mean, it doesn't look pretty, but there's no reason not to have it in that order. Okay. 2x cubed minus x fourth plus 2x minus minus x squared. I can't write. Okay. Okay. Times dx. What would that be? Anybody?
2x to the fourth over 4.
Okay, so 2x fourth over 4 and 2 over 4 would be x fourth over 2, right? Okay, minus
X to the fifth
over 5
over 5.
plus
It would be x squared.
plus x squared minus
X to the third over 3.
got it. And that's going from 0 to 1. All right. So that's going to be 2 pi times. Okay. Simply putting in the 1 is 1/2 minus 1/5 plus 1 minus 1/3. Right? 2 pi times. Least common denominator here is 30. Okay? And 1/2 would be 15/30, right? Minus 6/30, right? 1/5 would be 6/30, plus 30 minus 10/30. That's 30/30. Okay, 10/30. Right? Was that too magical? Is that all right? So if you add these two, that gives you 45/30. Minus 10 would be 35/30. Minus 6 would be 29/30. So 2 pi times 29/30, which that would be 29 pi over 15, I think. Let's see if that's anywhere close. 29 pi over 15. Good. You see how that works? Now, I see no advantage to rearranging this and getting in descending orders of power. Why? I mean, it's just extra work. So just go with the flow. Okay. Everybody got that? See how it works? Any questions on it? Okay. That finishes 7.3. Okay. Do homework exercises. I would say either 3 or 5. They're both at calcchat.com. And then do any of the odds 7 through 11. They're all at CalcChat, but 7's at CalcView. And then do either 13 or 15. They're both at CalcChat. And then any of the odds 17 to 21. They're all at CalcChat, but 17's at CalcView. Then do either 23 or 25. They're both at CalcChat. 23's at CalcView. Do 27. It's both at CalcChat and at CalcView. Then do either 29 or 31 or both. You choose. They're both at CalcChat. Do either 33 or 35. They're both at CalcChat. Okay. Then do, or at least take a look at 37. See what you can think through that. It should be at CalcChat as well. And then try 39. It should be at CalcChat as well. And then do 41. Comparing volumes, it should be at CalcChat. then either 43 or 45, they should both be at Calc Chat. And then some applied problems, any of the odds, 47 to, goodness gracious, 55, 47 to 55, and then there is 57 is a volume of a storage shed. I think you could do any of the odds, 59 or 61, either one of those. They should be both at Calc Chat. And then there's an interesting little project, the oblateness of Saturn. I don't know if y'all know what oblateness is. Do you? I don't know if this is the best word, but it sort of means fat, okay? Your planets are mostly spheroids. They're not perfect spheres, somewhat like a sphere, but they tend to be a little thicker in the middle, okay? That's what oblateness is. And Saturn is the most oblate of any of the planets, they say. And part of the reason for that, I think, is because Saturn has such a terribly small density. If you could have a pool of water big enough, Saturn would float. It's less dense than water. Of course, it's a gas, so it wouldn't really float, but if you did have it. So anyway, if you want to give a shot at that, you certainly can. It probably is going to be somewhat of a challenge, so don't get carried away with it unless you're really into doing that. All right. How are we doing time-wise?
Pretty close to a minute or two.
It's what?
I think we're pretty close. Like,
Awfully close.
yeah, 3
So,
minutes. Yeah, 3 minutes.
huh? 3 minutes. Less in the slideshow here. And, well, I'm just going to basically introduce you to the next section. Okay, just really, really basics. It's 7.4 in this arc length. So we've had areas as an application, volumes using disk and volume using shells, and now arc length is going to be another application of your integration. So I don't want to get too wound up in this yet, but just to give you an idea, what we're first going to do is find the arc length of a smooth curve. That's going to be a little bit of a challenge, but once you do it, it makes pretty much sense. And then we're going to take that arc length and revolve it around something and come up with an area of a surface of revolution. Not a volume, but a surface, because you're just taking a length and revolving that, so that gives you a surface. So that will be the second part of this section, okay? And I think that's probably all we're going to have time for. So we will begin next time with the slide. Goodness gracious, where is this slide?
This is 5 corner. What do you see on that end?
There's, yeah, it's somewhere right here, but I don't see the exact words right here, but it basically is starting right there. So we'll go from that. And I think, oh no, I didn't. Let me erase that. And we'll begin there next time.
See you on Wednesday.
What's that?
See you on Wednesday.
Yes. All right. We will proceed from there. Take care.